Now that we've had a chance to look at and get a little more practice on a more difficult equilibrium problem, I want to talk about some general strategies when solving equilibrium problems. Your strategy should always begin with a balanced reaction. If a reaction is not given, then you must write one and balance it. Second, write the equilibrium expression. This is an important step that many students try to skip but often make mistakes because of it. When you write the equilibrium expression, you see what substances are important to the problem and which ones are not. Thirdly, make an ice table and look at your initial concentrations, and then determine Q if you can. Q, your reaction quotient, allows you to determine shift. But keep in mind, if you start out with only reactants, the reaction can only shift right. It can only go in one direction. But once the shift is predicted, the change in initial quantities can also be determined. Use the change in initial concentrations to find your equilibrium values and solve for the unknown. After you solve your problem, you should always go back and check your values. Sometimes the K expression is more complicated and needs to be solved with the quadratic equation. When this happens, simplify the equation and set it equal to 0. You can use Polysmelt on your calculator to get the possible X values. Now that we've gone through the steps, I want to go through an example. You can follow along on page 616. Suppose for a synthesis of hydrogen fluoride from hydrogen and fluorine, 3 moles of hydrogen and 6 moles of fluorine are mixed in a 3-liter flask. Assume that equilibrium constant for the synthesis reaction at this temperature is 1.15 times 10 to the second. What are the equilibrium concentrations of each component? We will go through the steps to work through this example. 1. Write the balanced equation for the reaction. We have hydrogen gas plus fluorine gas yields 2HF gas. Write the equilibrium expression using the law of mass action. 1.15 times 10 to the second, which is K, is set equal to the concentration of HF squared divided by the concentration of hydrogen gas multiplied times the concentration of fluorine gas. Step 3. List the initial concentrations. The problem gave us moles of hydrogen gas and fluorine gas, but they were both in 3 liters. So hydrogen gas has a concentration of 1.000 molar, and fluorine gas has a concentration of 2.000 molar. HF was not mentioned in the initial concentrations and can be assumed to be 0. Step number 4 is to calculate Q and determine the direction of the shift needed for equilibrium. But since in this example we don't have any products, the reaction can only shift right. Calculation of Q is not necessary. But number 5, we need to define the change needed to reach equilibrium and define the equilibrium concentrations by applying the change to the initial concentrations. H2 and F2 are a one-to-one relationship. So H2 will lose X and F2 will lose X. HF, however, will gain 2X. So H2 is 1.000 molar minus X, F2 is 2.000 molar minus X, and HF equals 2X. In step 6, we will substitute the equilibrium concentrations we just solved for back into the equilibrium expression and solve for the unknown. It should look like 1.15 times 10 to the second equals 2x squared divided by 1 molar minus x times 2 molar minus x. When you simplify this equation with Polysmelt, you should get A equals 1.11 times 10 to the second, B equals negative 3.45 times 10 to the second, and C equals 2.30 times 10 to the second. When you plug this into the Polysmelt on your calculator, 2 values are possible solutions. X equals 2.14 molar or X equals 0.968 molar. But only 0.968 molar can be valid since the other value would lead to a negative concentration on one of your reactants. Now we need to apply X, the change that you just solved for, to your equilibrium values. Hydrogen gas is 1 molar minus X, which gives us 3.2 times 10 to the negative second molar. Fluorine gas was 2 molar minus X, which gives us 1.032 molar. And finally, HF was 2X, which equals 1.936 molar. Step 7 is to go back and check your calculated equilibrium concentrations by making sure that they give the correct value of X. When you check your answers, you will find that these equilibrium positions give you 1.13 times 10 to the second. This is a close agreement to the given K value in the problem. Let's try one more. Practice problem number 12 is on page 617. Assume that gaseous hydrogen iodide is synthesized from hydrogen gas and iodine vapor at a temperature where the equilibrium constant is 1.00 times 10 to the second. Suppose Hi at 5 times 10 to the negative first atmosphere, hydrogen gas at 1 times 10 to the negative second atmosphere, and I2 at 5 times 10 to the negative third atmospheres are all mixed in a 5-liter flask. Calculate the equilibrium pressures of all species. Step 1. Write the balanced equation. Hydrogen gas plus iodine gas equals 2Hi gas. Step 2. What is the equilibrium expression? 1 times 10 to the second equals pressure of Hi squared divided by pressure of hydrogen gas multiplied by pressure of iodine gas. What are the initial pressures? If we go back and read the problem, it says suppose Hi at 5 times 10 to the negative first atmospheres, hydrogen gas at 1 times 10 to the negative second atmospheres, and iodide gas at 5 times 10 to the negative third atmospheres are all mixed in a 5-liter flask. These are all given pressures, so the volume of the flask does not make a difference. So the pressures are as given. Step 4. What is Q? Q is equal to the pressure of Hi squared divided by the pressure of hydrogen gas and the pressure of iodide gas multiplied together. When we take the given given pressures for these species, Q will equal 5 times 10 to the third. Step 5. What is the change required? If Q is 5 times 10 to the third, then Q is greater than K, and the system will need to shift left to reach equilibrium. This means that our products will lose X and our reactants will gain X. Hydrogen gas starts at 1 times 10 to the negative second atmospheres plus X. Iodide gas will be 5 times 10 to the negative third atmospheres plus X. And Hi, our product, will be 5 times 10 to the negative first minus 2X. Step 6. What is the value of Kp and the equilibrium pressures? Kp is equal to the law of mass action and substituting in our change values. Simplified, we will have 9.6 times 10 to the first x squared plus 3.5x minus 2.45 times 10 to the negative first equals 0. X, therefore, will equal 3.55 times 10 to the negative second atmospheres. Once X is found, our equilibrium pressures can be found. We apply the change to each of the individual concentrations. The pressure of Hi, 5 times 10 to the negative first atmospheres minus 2X equals 4.29 times 10 to the negative second atmospheres. The pressure of hydrogen gas, 1 times 10 to the negative second atmospheres, gains the change of 1X equals 4.55 times 10 to the negative second atmospheres. The pressure of iodine gas, 5 times 10 to the negative third atmospheres, also gains 1X for 4.05 times 10 to the negative second atmospheres. Once we have found the equilibrium positions, it's time for a reality check. We take our answers and apply it back to the law of mass action and make sure that it equals K. This is an easy way to double check your work and not lose points. This concludes the third video in the equilibrium series.